talking all about probability for the next 4 sections. You do need a calculator, basic calculator, graphic calculator, any of those are fine. When you're writing on those screens, remember you can detach the keyboard. It's magnetic. You can just pull it off. And then you can always make the screen a little bit flatter too, if you want to. It totally won't break it. Yep. Okay, so we're going to go into our weekly folder in Polaris. Just like log in, and then you're looking for under notes. It's 3-1 Jamboard, and it's going to look like the slideshow that I've got up here. Just get logged in there. If you want to. Just let me know if you run any trouble as you're using it. We'll kind of work through the kinks. All right, so 3-1 is going to be basic probability, counting principles, that sort of thing. So we're going to start just with the definition of what is probability. Probability is the branch of mathematics that calculates, estimates, or simulates the likelihood of a given event. So that's going to be the big idea around this. If we're calculating the probability, we're calculating how likely is this event to happen. We're going to start talking about probability experiments. A probability experiment is some sort of trial or action or an experiment where we're counting the results in one way or another. The results of a single trial are called an outcome. So an outcome is something that could happen one time as you're completing this experiment. And then it's possible as we repeat the experiment or the trial over and over again that we get different outcomes. The different outcomes then make up what we call the sample space. An event is a subset of the sample space. It may consist of one or more of the outcomes. So sometimes we use the word event and outcome kind of interchangeably because they both could represent one possible result of a trial. So a lot of common things that we're going to see over the next couple weeks are drawing cards, rolling dice, flipping coins, spinning a spinner, that sort of thing that you guys talked about. Maybe if you've done probability in the past, we're going to see some of those things come up again. Okay. Questions on this? Okay. So the first thing we're going to do is practice making a set of outcomes and creating that sample space. So we have a survey that is asking people for their blood types, which there are 4 options for that: O, A, B, and AB, and then whether they are either Rh positive or Rh negative. So for example, if you know your blood type is AB positive, your blood type is AB, and your Rh positive is what that means. Okay, so we need to identify the outcomes, and then we'll count up how many outcomes there are in our sample space. All right, so the first thing they're asking people is what are their blood type? There are 4 options for that. So we'll make like a little branch here. Blood type. And then we're going to have 4 branches, 4 possible answers to that question. O, A, B, and AB. From there then, depending on how they answer, there could be, in addition, 2 more things coming off of each branch. Somebody could be either Rh positive or Rh negative. So for example, if my blood type was O, I could then be either O positive or O negative for that second question. And then A would be either A positive or A negative. B positive, B negative, A, B positive, A, B negative. And that last line there, sometimes we put it with brackets, sometimes we put commas between it, makes up what we call our sample space. Okay, so your sample space is the set of all possible outcomes, and then each option within there is an outcome. An event would be an example of maybe multiple outcomes happening back to back. Like maybe if I interview 2 people And an event could be that 2 people in a row answer that they have blood type A. That could be an event. So it's possibly a combination of 2 outcomes happening at the same time or back to back or consistently or something like that. All right, so sometimes if you're doing like your math Excel, they might refer to this as like a tree diagram. You can see that. That's what we're doing here. We're just starting with the first option and branching out from there with all of our possibilities. So if you had to answer how many outcomes are in the sample space, how many outcomes would be in the sample space here? 8 events in the sample space. Good. Okay. How are our tablets working? Going okay? Any questions so far? Great. Okay. All right. So next question. We want to know, does your favorite team's win or loss affect your mood? Yes, no, or not sure. So for each probability experiment, determine the number of outcomes that identify the sample space. So we'll do the first one together here, and then I'll let you guys try the bottom two. It says a probability experiment consists of recording a response to the survey statement at the left, which is, I put it at the top here for you guys, and then the gender of each respondent, okay? So again, you can start with the tree diagram. The first question that's being asked is, does your team's win or loss affect your mood? Yes, no, or not sure. So yes, no, or not sure are the 3 possible options to start. From there then, we're gonna get the gender of the respondent, and we're just gonna stick with male and female right now, okay? So male, female, male, female, male, female. Okay, so there are 6 possible outcomes. If you're going to list the sample space, then that last row is going to consist of it. Now, I need to have a way to distinguish between somebody that answers yes and is male and somebody that answers no and is male. So a lot of times we abbreviate things like this. So, in front of those first 2, I might put YM and YF, just to say they answered yes and they're male, or they answered yes and they're female, or no male, no female, and then I'll put maybe NS for not sure, NS for the males. Okay, and then again, 6 outcomes in that sample space. Okay, make sense? If you don't need to do the tree diagram, if you can just list out all the possible outcomes, you can go straight to that. The tree diagram is just kind of optional to get you from point A to point B. All right, so using that top question and an additional piece at the bottom, try numbers 2 and 3 real quick on your own, okay? Let's check our answers. You should have 9 and 12 number of outcomes in the sample spaces for those. And then I just abbreviated the first letter on each is either yes, no, or if it's an NS for not sure. And then whatever the second bit of each of those is like the age group, just put 50 plus or 15 older, or geographic location. Now, if all you needed for these was the number of outcomes in the sample space, this is definitely the long way to do it. So I'm hoping you notice that these are all multiples of 3, because the first question had 3 possible answers to it, yes, no, and not sure. And then from there, the first question had 2 additional responses, so 3 times 2 gives us 6. Or the middle question had 3 additional responses, 3 times 3 gives me 9. And the last question had 4 additional responses, 3 times 4 gives you 12. So that's called the multiplication counting principle, which says if I have this many options for question number 1, and I have this many options for question number 2, all I have to do is multiply those together, and that's going to give me the total number of outcomes possible for that survey or trial or whatever I'm doing. Okay, so that's actually our next definition here. I'll come back to that other slide in a second. It's officially called the fundamental counting principle. Again, you might call it the multiplication counting principle. If one event can occur in m ways and the second event can occur in n ways, the number of ways that the 2 events can occur in sequence is m times n. So like our questions were 3 times 2 or 3 times 3 or 3 times 4, and that's where we're getting the total number of samples. So in this example, it says you are purchasing a new car. The possible manufacturers, car sizes, and colors are listed in the table. And we just want to figure out how many different ways can you select one manufacturer, one car size, and one color. Again, you could make the tree diagram out of this. You would start with 3 branches for manufacturer, and then each of those branches would have 2 coming off of it, and then each of those would have 4 coming off of it. Again, that's going to be pretty tedious. Instead, we can just say, how many choices do I have for manufacturer? 3. How many do I have for car size? 2. And how many do I have for color? So there are 24 different ways that we can make a selection of a car. And again, if you drew the diagram, you would have 24 branches at the bottom of your diagram if you decided to go that route. But if we don't need all of those possible outcomes, this is definitely a more efficient way to do it. Okay? So fundamental counting principle, multiplication counting principle. Do you guys remember doing that in, like, I don't remember when you would have seen that, like pre-algebra maybe? You do a little bit with this? Does this look familiar at all? You might have done it with, like, menu items. Like you could choose this many appetizers. This many. No? Like clothing, outfits. Yeah, I'm trying to remember, like, common examples that you would use in other math classes with this kind of stuff. Yeah, that's a good example. Okay, so the next slide then is one that we're going to see a lot. It talks about, like, access codes or pins, things like that. So here we have an access code for a car security system, and it's going to consist of 4 digits. And if they don't tell you, you're going to assume that the digits are the numbers 0 through 9. So how many digits are there if we include all the numbers from 0 through 9? There are 10 digits. And sometimes they'll tell you don't include zeros or something like that, so that would make it a little bit smaller. So the first question is, how many access codes are possible when each digit can only be used once and not repeated? Okay, so we want to think about how many choices we have for each digit. So let's start with the first digit. I haven't used any digits yet, right? So how many choices do I have? 10, okay? Then I'm not allowed to repeat. So whatever I use for the first digit, I cannot use that for the second digit. So how many choices do I have? 9. So for the third digit, I have 8, and for the fourth digit I have 7. And then this is where you need your calculator. Multiply them together. 10 times 9 times 8 times 7. 50, 40 are the possible number of access codes. What about if each digit can be repeated? How many choices do I have for the first digit? 10. How many choices do I have for the second digit? 10. Third, 10, 10. That's quick math, 10,000. Okay. What about if each digit can be repeated, but the first digit cannot be a 0 or a 1? So how many choices do I have for the first digit? 8. And then for the other digits I have, so it said each digit can be repeated, but only the first digit can't be a 0 or a 1. So the other ones could be a 0 or a 1. So it's going to be 10 for each of those. So 8,000 I can get for that. Okay, does that make sense? All right, so hop to the next slide. I want you guys to try these 4 again. You might need a calculator to do the multiplication at the end of these. So here they're doing license plates. So they're talking about alphabet letters and digits. All right, so see if you can find the number of possible combinations. All right. Let's connect to the internet, shall we? Here it goes. All right, so I abbreviated here a little bit with my exponents. You don't have to do that, but the first one you're going to multiply 6 26s together, so I just did 26 to the 6th power. Number 2, it cannot be repeated, so that's where we do 26 times 25 times 24, et cetera. Number 3, the first one cannot be the first 4 letters of the alphabet, so 26 take away 4 leaves me with 22, but everything else can be any letter, so times 5 26s, or 26 to the 5th power. And then my last one, the first one has to be a digit 1 through 9, so I only have 9 options for the first part of the plate, and then again, it could be anything after that, so 5 26s multiplied together. What questions do you have on those? Anything? Yes.
The second one, why do you only go to 21? Can't you just be on that?
Because we only need 6 letters. There's only 6 choices for the plate.
On these, is there like a way to like, I don't know, like make the background bigger, just have like more like word space? You know what I mean? You know,
I'm
like,
with you on that. I don't know if you guys can make it more full screen than it actually is. Something I can do on my end if I'm making them, and if I can take like what I have on one slide up here and split it into 2 slides on your end, so that creates a little space naturally.
Okay, yeah.
Does that make it help
Yeah,
a little bit? Okay.
yeah,
All right. We're just working through the kinks. We'll
yeah,
figure it out.
totally, no, I got it.
Yeah. Yeah, I get that. Okay, any other questions? Okay, cool. All right, moving on. Okay, so next thing we need to talk about is different types of probabilities. There's 3 main categories we're going to have for probability. We're going to have either subjective probability or objective probability, which we don't really use the word objective very much. We more so just use the 2 categories within it, classical and empirical. So when you're doing homework problems, you're going to be asked this, and it's going to be pretty much a multiple choice question. Is this type of probability either subjective, empirical, or classical? Okay, so definitions of those. We're going to start with, oops, maybe if it wants to go, there we go, classical. So classical is sometimes called theoretical probability. It's what in theory should happen. So we use like rolling a dice or drawing a card, things like that often because we know how many are in the set and what should happen based on what I am looking for in that specific outcome. So notation that you're going to see here, you're going to see P of E right now, but that could be anything inside the parentheses. So the capital P with the parentheses means the probability of, and then whatever is inside the parentheses is the event that you want to happen. So right now they're just calling it event E. In general, though, this should be familiar to you. If we want to calculate the probability of something happening, it's how many times it can happen divided by how many total things could happen, how many total outcomes are possible. So for example, if I wanted to know the probability of drawing a, I don't know, ace of hearts out of a deck of cards, my theoretical, my classical probability would be a 1 out of 52 because there's 52 cards in a deck and there's only one of those in the deck. And then you could leave it as a fraction or you could turn it into a decimal. So we're going to run through these ones kind of quick here. It says, first, let's say you're rolling a dice. What is the probability of rolling a 3? What do you think? Yep, there's 1 on the dice. There's 6 possibilities. 1 out of 6. What is the probability of rolling a 7? 0. Yeah. So if it is impossible for something to happen, my probability is 0. What is the probability of rolling a number less than 5? So what numbers less than 5 are there on a die? 1, 2, 3, 4. So 4 out of 6. And then if we have a fraction that can be reduced, we want to reduce that 2/3. And again, you can also give the decimal. Math Excel, I think they're going to use decimals more than fractions. So you could divide that, and it would be 0.667. Okay. You select a card from a deck of playing cards, and we want to find the probability of each event. So the next event is selecting a 9 of clubs. How many 9 of clubs are in a deck? 1 out of 52. How many hearts are in a deck? There are 13 of each suit. Yeah, so 13 hearts, 13 diamonds. Just take that 52 and divide it by 4. And then what is the probability of selecting a diamond, a heart, a club, or a spade? Even more than that. Yeah, 52 out of 52. Everything in the deck is either a heart or a club or a spade or a diamond, so my probability is 1. So what's the smallest probability you can have? Something being impossible? 0. And what's the biggest probability you can have? A certain event? 1. 100% if we put in a percentage, yeah. Okay. All right, the next definition is empirical probability. Empirical is sometimes called statistical probability because it's based on the results of an experiment. But again, the formula is still going to be the same. It's going to be how many times something pretty much did happen divided by how many things happened in total. And our notation is still the same. We're going to use P and then a parentheses to represent probability of a certain event occurring. Okay, so little pie chart at the bottom. This is a quick one. We've got a survey results. This is book reading by U.S. adults, and it tells you how many read different kinds of books. The question is, what is the probability that the next adult surveyed read only print books during the last year? So how many adults only read print books? 578 divided by the total number of adults that were surveyed, which actually they give us that information in the little blurb. What is that? 1490. So we can leave it as the fraction. I'm going to turn this one into a decimal. 578 over 1490. And I get 0.388. 3 decimal places, pretty standard, round to the nearest thousandth on these. Okay, so again, the frequency really of that event, how often it occurred, divided by n, the total number in our sample space. So we saw those variables pop up in our last chapter. Those are going to be happening again. Okay, so classical is based on theory. Empirical is based on an experiment. We're going to skip over this slide. The third one is subjective probability. Subjective probability is based on a guess, an intuition, or using previous data to make a hunch or an assumption. Okay. So on this slide, we're going to just categorize what kind of probability each of these experiments or questions represents. So the first one is the probability that you will get an A on your test is 0.9. So is that based on theory, do you think? No. Is it based on an experiment? No. Is it based on a hunch? Educated guess? Yes. So that's what we call subjective probability. The probability that a voter chosen at random will be younger than 35 years old is 0.3. Okay. Is that based on an experiment? Yes. Do we know there's been an experiment run? Not necessarily. Is it based on a guess? Educated guess? Potentially. This could be subjective. It could be also theoretical. So classical probability here as well. It depends on what information they're using to make this guess. If they're just saying, we think there's this many people, and so based on previous years, it's subjective. It could also be classical here, though, if they have like data to show how many people are in the set. So I'm just going to leave that one kind of open for interpretation. I feel like we do need a little more information on that one. Probability of winning a 1,000-ticket raffle if one ticket, or if one ticket is a 1 out of 1,000 chance. What do you think for that one? Kind of like the dice one, right? The probability of rolling a 1 is a 1 out of 6, right? What kind of probability was that? That was classical probability. or theoretical probability, what should happen. Okay, and again, this one could be classical. I mean, I don't know. I'm just going to leave that one blank. I don't love that question very much. Okay, what are the things we jumped over? Slide before this, law of large numbers. Law of large numbers says as you complete an experiment, the total probability that you receive for a certain outcome will eventually reach the theoretical probability of it happening. So for example, they've got probability of tossing a head if you throw a coin up in the air. If I throw a coin up in the air, the theoretical probability is I have a 50-50 chance of getting a head. But it's very likely that I'm going to throw it and I'm going to get a tail. And I might get a tail again. I might get a tail again. So that does not equal what the theoretical probability is. But the law of large numbers says if I keep tossing that coin, the more I toss the coin, the more it's going to be that the probability or the number of heads I get ends up being that 50% number that we expect with the theoretical probability. So this is why we like to repeat experiments, because the more we repeat the experiment, the more that the probability we get is actually the true probability. Okay? All right.
What's the law of big numbers?
That was the law of large numbers. Large numbers, yes. So it just says the more that you repeat an experiment, the more the probability you get for a certain outcome reaches the theoretical probability. So if I roll a die, if I want to get an even number, the probability is 50%. But if I do it 5 times, I'm not necessarily 50% of the time going to get, well, I'm not, if I roll it 5 times, 50% of the time going to get all even numbers. But the more I roll the die, if I roll it 1,000 times, it's more likely that my even numbers will approach that 50% number. Okay, so they kind of show that in the picture here. You kind of bounce around what that theoretical probability is, and it kind of gets more linear as the experiments or the number of tosses of the coin here get larger. Okay. All right. We already talked about this. Our range of probabilities is 0 to 1. 0, never going to happen. 1 is certain. Down below, we've got definition of a complement. Definition of a complement is the opposite to everything else. So if I toss a head, what's the complement of that? Tails. If I roll a 1 on a dice, what's the complement of that? It's everything else besides a 1 is the complement. So it would be 2, 3, 4, 5, 6. The probability of an event plus the probability of its complement, which we're going to use this little tick mark here, is equal to 1. Because the probability of an event is just P of E, and the probability of our complement is everything else. In total, they will equal 1, being certain either one will happen or the other. So they give this picture a lot. Sample space is our rectangular region, and then it's divided really into 2 pieces. You're either in the circle or you're not in the circle. Okay, make sense? Okay. So last example, using the frequency distribution chart to the right, find the probability of selecting a social networking site user who is not 23 to 35 years old. So option number 1 is I could add up all of the other categories here and then divide that by the total. Option number 2 is I could find just the probability of my 23 through 35-year-olds, which there's 312 of those out of 975 total. And I want everybody except that group. Well, if I have that, I'm calculating a complement. So I can just take 100% of the possibilities, subtract off what I don't want to happen, and what I'm left with is everything else, which will ultimately end up being all the other categories summed up. But it's a quick way to calculate something if you have a complement. You can calculate a probability of one thing and then just 1 minus that to get the other. You know that they are complements of one another. So 1 minus 312 over 975 Gives me 0.68. Okay, so it can help you. It'll give you a little shortcut at some problems if you notice that complementary relationship. All right, and that is it for section 3.1. Okay, any questions? So Math Excel is due on, do I have many calendars here? I do. So technically this is a no homework weekend. Our Math Excel is due Wednesday night next week. So I mean, if you want to work on it, you can, but by all means, take the weekend off. You've got time next week to do that. All right, and then next week we'll play with these a little bit more. We'll maybe give it another week, trying with the Jamboard, see how it works, see if we like it. We'll go from there. We'll see what other kind of fun things we can do with these devices. So whenever you're done with it, you can take that document in your Google Drive, put it where you want it if you haven't already, save it, and then you've got that anywhere you go, ready to work on your homework, which is pretty awesome.